Today I'm going to do an overview of a paper that I wrote recently called Simplifying and Refactoring Introductory Calculus. So when I talk about refactoring in computer programming, we have this concept called refactoring, and what it means is that we rethink kind of the way that we do our basic tools. So if you think about factor in math, you know, you have you reduce a number to its prime factors. Well, sometimes there's in more complicated things, there are more than one ways to break a process down into its constituent parts. And you know, in factorization, there's only one way, but in processes, there's oftentimes several different ways to accomplish the same thing. And so, refactoring just means breaking something down into different components. So if you imagine, let's say that we have an inefficient process for welding. Well, refactoring will say, okay, well, let's think about how we do a weld. Let's think about what are the different steps in the process. Are there any that we can combine? Are there any we can throw out? That's what refactoring is. So when I say I'm refactoring calculus, what I really mean is that I am taking the steps and seeing if there is any way that we can do it. When I say refactoring calculus, what I'm doing is I'm saying, are there any steps that we're doing that are not needed? Or in this case, mostly what I'm focused on is whether or not there are we're repeating information that we don't need. Are we causing students to have to think about too many things, or can we reduce the cognitive load without reducing any of the things that a student can do with calculus? So to do this refactoring, the first thing that I came up with was that we need to move from doing derivatives to differentials. You know, most of you have learned the, I'm sure most of you know Leibniz notation. So Lagrangian notation says that if I have, you know, y equals x cubed, in Lagrangian we would say y prime equals 3x squared. Leibniz notation instead is dy over dx equals 3x squared. And they really mean the same thing. The thing that I like about Leibniz notation is that we're more specific about what we're talking about. First of all, in this case, you can notice that on the left-hand side, y prime, what does that mean? Some other y? It's very ambiguous. In fact, this derivative is being taken with respect to x, but it doesn't say that anymore. So if this were a multivariable equation, we wouldn't know what value this was being taken, this derivative was being taken with respect to. On this one, however, we're very explicit. We're saying we're looking at the ratio of the differential of y to the differential of x. Okay, so we're being a lot more explicit. And you can do a lot more with this too, because this is a ratio and it is a fraction. You can actually split the fraction as well. So I can rewrite this as dy equals 3x squared dx. And what I'm saying is that the differential of y is equivalent to 3x squared times the differential of x. That is the way. So what is a differential? Well, a differential is an infinitely small change in something. So what this is saying is that if I have an infinitely small change in my y variable, then that's going to correspond to an infinitely small change in my x variable, but it's not going to be a linear. It's the amount of change between these two is going to depend on where I am on the x-axis. So at different parts of the x-axis, the ratio between my changes in y's and changes in x are going to vary. So for example, if we say, at x equals 2, then dy will be equal to 12 dx, which means that for any infinitely small change in y, the infinitely small change in x will be 12. Any infinitely small change in y will be 12 times bigger than any infinitely small change in x. So that's what that means. So by splitting it out this way, you can do some really cool things. First of all, notice that we're simply referring to the variables here. Here, y prime had a notion of a change in x within it, but here we're just talking about y over here, and we're just talking about x over here. So what can we do to that? Well, we can actually rewrite all of our differential rules in terms of, or we can rewrite all of our derivative rules in terms of differentials. So, let's say that we have our typical rules is if you have, y equals x to the n, then y prime equals n times x to the n minus 1. All right, well, that's interesting, but you can actually rewrite this as a differential rule. So again, let's get rid of our y prime, and let's instead call that guy dy over dx. Okay, so now I can multiply both sides by dx, say that dy equals n times x to the n minus 1 dx. So now I have, on the left side, I have the differential of the left side, and on the right side, I have the differential of the right side. So I've converted this from a kind of a heavy operation to a light operation. What I mean by that is that I can go from y to dy with just a simple operator. So we think of d, when we say dy, we don't mean d times y. It's actually a shorthand for d of y, the differential of y. Okay, so these two things are equivalent. And likewise, when we say dx, we don't mean d times x, we mean the differential of x. So if I have y equals x to the n, you can do anything to an equation as long as you do it to both sides. So I'm going to take the differential of both sides. Okay, and so using the same rule, so dy, we said earlier that dy is just another way of saying the differential of y. So I can write this as just being dy, and that's equal to, so here, if we took the differential of this side to get that, then when we take the differential of this side, we'll get this. So the differential of y equals n times x to the n minus 1 dx. So you can see that our sides are actually operating independently of each other, as are our variables. This guy doesn't have to know anything about y, and this guy doesn't have to know anything about x. They are completely independent. So why is that important? Well, it makes it very easy to move our differential rules into multivariable versions. So, so let's just list out a few more differential rules. So using the format that I did earlier, and you can prove this the same way just by transforming your derivative rules into differential rules. We have differential of a constant, still equal to 0. The differential of x to the n is n times x to the n minus 1 dx. The differential of u plus v equals du plus dv. And the differential of u times v equals u dv plus v du. So these are pretty standard rules, but let me show you how you can apply these. So let's say that we have y squared equals 3z squared plus 4x cubed. Okay, so this is now a multivariable equation, and it's an implicit function because it's not a function of anything. But you can use your standard differential rules as before. So what we can do is you can do anything that you want as long as you do it to both sides. So we'll take the differential of both of these sides. So the differential of y squared, well, that uses that rule. So the differential of y squared is 2y dy. And that is equal to, well, using our addition rule, we can see that we can separate these guys at the plus sign. So what's the differential of 3z squared? Differential of 3z squared is going to be 6z dz. 6z dz. And the differential of 4x cubed is equal to 12x squared dx. So now we have solved, so now we have a differential that is multivariable. So now what we need to do is, we really want a derivative because these are nice, but they're all infinitesimals. So to get a derivative is simply a ratio of infinitesimals. So you have to decide what variables do you want a derivative of. So let's say we want to go and do our standard dy over dx. So what do? Well, you divide both sides by 2y to get your dy by itself. So let's get rid of that. So we'll divide both sides by 2y. Actually, let's split this to make it easier. 2y. So this 2y will cancel. And then we'll divide both sides by dx. And these will cancel. So then that gives you your final result. Rewritten nicer, we can say dy over dx equals 6z dz over 2y dx plus 12x squared over 2y. And so what does this say? Well, this says that the ratio of change, the rate of change of dy to dx at any given point is equal to this formula. But interestingly, this formula also has a ratio of differentials in it. So basically the slope here depends on which of these slopes you're looking at. So if you're looking at a particular slope here, that will tell you if you're looking at a particular slope over here, that will tell you which particular slope you're going to wind up getting over here. And so as you can see, you can very simply switch from single variable to multivariable calculus without doing any additional work whatsoever. Interestingly, you also get rid of the chain rule. So for example, let's say we have just a simple one. We'll do y equals 2 to the, let's see here. Actually, let's make it even easier. Let's say e raised to the 3x power. Now, normally you would solve this with the chain rule, and that's perfectly legitimate, but we can show how the chain rule is actually just a result of basic algebra. So the rules that we're going to use is the differential of some constant times u is n times du, and the differential of e to the x is equal to e to the x dx. Actually, I should probably use u in that. So e to the u equals e to the u du. Okay? So now, what do we do here? Well, you can see that this does not follow either of our standard forms. But we can transform the equation so that it does. So what we can do is we can take this 3x and assign it to a variable. So let's just call the variable q. So we'll say q equals 3x. So now our equation becomes y equals e to the q. Okay, so fair enough. So now, math doesn't care what you call variables. So e to the q is just like e to the u or e to the x or any of those other things. So if I can take the differential of both sides, and I will get dy equals e to the q dq. And that is exactly matching that rule. Okay, so this is a valid answer. It's just not in the form that we really want, because our question was in terms of x, and we answered it in terms of q, which is our made-up variable. So now what we have to do is we have to substitute back in. Well, it's easy enough to substitute in for q because we have an equivalency right there. But what about for dq? How do we substitute that guy back in? Well, we have an equation here for q, so how do we get from equation for q to an equation for dq? Well, we just take the differential of both sides. So d of q equals the d of 3x. Differential of q is the same as the differential of 3x. And that's going to give us dq equals 3 dx. So now that dq can be replaced by that formula. So then our final result is dy equals e to the q, which is 3x, dq, which is 3 dx. Now I probably want a derivative, so I'll divide both sides by dx, and that will give me dy over dx equals 3 times e to the 3x. Okay, so you can see how doing, you can tell that this is actually the same as the chain rule because we're multiplying by the differential at the end. But we didn't actually have to establish a formal rule for it because it's just basic algebra. We know that if things are equal, you can substitute them in, and we know from basic calculus that you can take a derivative of something. And so using those two ideas, you can just get rid of the chain rule as a rule and just use basic algebra and basic algebra conceptions to do the exact same thing. Okay. So you might have noticed that we've been treating differentials algebraically. So we've been multiplying and dividing by them, and some people throw a hissy fit about that, and that's cool. I understand that. That's from in the 1800s. There was a movement to make calculus more rigorous, and they didn't have a rigorous way of understanding differentials, so they replaced differentials with limits of fractions. But in the 1960s, we found out that we actually could use differentials as actual entities, and so now you can use differentials algebraically. There's one problem though, and that is second differentials. So I'll do that in a different video, but for right now, just note that you can freely manipulate first differentials. But just be careful that you're doing first differentials. You actually can freely manipulate second differentials, but you have to correct for a common error that has been made in the development of calculus notation. And we'll do that in a different video. Another thing that we'll put in a different video is that you can also simplify integration to some extent using the notion of differentials. But we'll save those for another time. I think we've done enough work here. So anyway, so to simplify calculus, we're switching from derivatives as the primary thing that you find to differentials. And by making this switch, we're able to extend simple derivative rules to apply them equally to single variable multivariable and implicit derivatives. And tagged onto that, you also get the chain rule for free. It's not a separate rule, it's just implicit in the way that you do things. So that's why I like to refactor calculus and use differentials instead of derivatives, because it makes the whole process much simpler, and you can use a single standardized process for all of your different types of differential, all of your different types of derivatives. So anyway, we'll do other videos for how to simplify other parts of calculus, how to do second order differentials, and that sort of thing. But for right now, I'll leave you with that.